Hello friends, welcome to my channel. Today we are going to talk about a very amazing phenomenon which is called the hydraulic jump. Okay, and the title of the problem is an unsinkable disk. Okay, so why the title of the problem is an unsinkable disk? If we are going to talk about an hydraulic jump, okay, we will discuss that later in our lecture. Here you can see that water is flowing at a very high speed from the gate of a dam. Okay, you can just see the water is flowing at a very high speed from the gate of a dam, and here there is a very thin layer of water, very thin layer, and then you can just see that there is a abrupt rise in the layer of the water, abrupt jump in the layer. Okay, abrupt jump, you can just see the abrupt jump h of height h. You can just see here there is a height h. Now why this abrupt jump is observed? Okay, this abrupt jump is observed due to the phenomenon of hydraulic jump. Okay, so let us discuss more about hydraulic jump. So in the case of disk, we just do not see the regular linear hydraulic jump which we see here in a dam. That is a linear hydraulic jump, linear hydraulic jump. Okay, but in the case of a circular hydraulic jump, there are many hydraulic jumps in a circle. Okay, there is a locus of hydraulic jumps. Okay, and there are number of hydraulic jumps in a circle. Okay, so there we see that what is the real meaning of circular hydraulic jump. Okay, you can just read this question and comment down from where I have got this question. Okay, so this is a question taken from a very nice book. Okay, you can just comment from where I got it. So today I will discuss the given problem. Okay, you can just see that what is a circular hydraulic jump. You can just read the question, pause for 2 to 3 minutes, and then just comment down what you think is going to happen, and then just see the solution. Okay, so here you can see that the question is asking you that a very high flow of water, or you can just say a water jet, is falling on the central region of a submerged disk. Okay, so this central region here, as you can see here, the central region, there is a very thin layer of water over the disk. This layer, as you can see, this is a very thin layer which is flowing outwards. The water is flowing outwards from here, water is flowing outward from here, radially outwards, from here, in that direction, 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 here, in outwards to the screen. You can just see it's pointing outwards to the screen. Okay, in the outwards to the screen, there everywhere the water is flowing outward in radially outward direction, and then suddenly an abrupt jump is observed. This is called the hydraulic jump. Now our task is to determine that why the disk is not sinking, even of the large force that is acting on it, the impulsive force due to the water jet. And the second part is finding the location of the hydraulic jump. Where is hydraulic jump located? Okay, so you can just do pause the video and start solving the question, or you can just continue and see the solution. Okay, so as you can see, there is a large impulsive force acting on the central region of the disk, and there is a hydraulic jump also observed at a radial distance from the disk. Okay, at a radial distance from the disk. So this is the remaining part of the question. You just do, and here it is written. Now for the question, why does the disk not sink under the pressure generated by the powerful water jet? Okay, we will discuss the solution here. First we will discuss the radial function which defines the hydraulic jump, or at what radial distance from the center of the disk hydraulic jump will be located, or the location of the hydraulic jump. So the hydraulic jump following the impact of a liquid jet on a plate is a very common example of free boundary problem in fluid mechanics. You just studied that. Okay, I will give you an example, and that is written here. Once you turn on the tap of a sink in your kitchen, you can just see there is a very thin layer of water. You can just see a circle forming out there. Okay, and a very thin layer of water flowing through the center of the circle to the circumference of the circle, and there you can see an abrupt rise which is called the hydraulic jump, as we will discuss it in this particular video. Okay, at some distance from the jet, however, the height of the liquid suddenly jumps to a higher value. Okay, so here we will just observe that the rate of the flow determines the location of the hydraulic jump. Okay, so here we can just see that uh, general analysis. What is the general analysis of the hydraulic jump? Okay, So here we will see the general analysis of the hydraulic jump. Okay, so the hydraulic jump is a very interesting phenomenon, and you can just investigate both experimentally and theoretically. Okay, so we will discuss only the last part, that is the radius r of the circular hydraulic jump as a function of the impact speed, volume flow rate, density and viscosity of fluid, the boundary conditions governed by the size and the geometry of the plate. We will discuss that here in our today's video. Okay, so this is the general analysis of the video. Okay, so all the turbulent flow, eddy formation, energy loss, that will not study here. We will just study the general analysis. Okay, so first we will do the flow analysis. Okay, what's the flow analysis? In the central region of the horizontal radial flow, as I told you, you can just read it, I'll just tell you the summary. The water on the surface of the disk, the thin layer on the surface of the disk is in contact with the air. So the air is exerting an atmospheric pressure, and the force on that is the atmospheric pressure multiplied by the area of the upper face of the disk. Okay, and in general the flow which is observed here is laminar due to the viscosity, and the decrease in depth of this layer does not exactly follow the simple inverse proportionality rule. Now what is this inverse proportionality rule? The inverse proportionality rule is the continuity equation applied to the uh, flow. Okay, you can just see that the continuity equation is applied here. Now what's the force analysis? The force analysis says that the vertical water jet pushes the disc down with a large impulsive force. Okay, you can just see that the central region of the disc is just pushed by a large impulsive force which is created by the water jet. Okay, this is called the hydrodynamic pressure. Now hydrodynamic pressure is created due to the impulsive force. Okay, impulsive force. Now the hydrodynamic pressure just pushes the disc downwards, and the weight of the disc is also acting downwards. So why we just can't say that the disc will sink, because all the forces are acting in the downward direction. So this is the problem, that you have to find why the disc is not sinking and what kind of upwardly force is acting on the disc, that is balancing the downward ones. Okay, so here you can just see a diagram that I have made here. Okay, here is the layer of the water. Okay, layer of the water which is flowing radially outwards on the top of the disk. It is a very thin layer, and here the atmospheric pressure is acting F naught. The location of the hydraulic jump is shown by the small r, and the radii of the disk is shown by capital R. The d is the diameter of the jet. Okay, the diameter of the flow. V is the velocity of the flow. The F impulsive acting on it, is shown by the FIMP, and the height of the hydraulic jump is shown by h, and the mass mg is shown at the center of the mass of the disk. Okay, and what is this F? This is not the hydrodynamic pressure, but it is the hydrostatic pressure which is acting on the lower half of the disk, okay, lower face of the disk. And the hydrodynamic pressure is acting on the upper half of the disk, or the central region of the disk, from where the water flows in thin layer in radially outward direction, and then results in an abrupt rise in water, which is called the hydraulic jump. Okay, so I have just written the continuity equation, dmv by dt, and here I got rho, which is the density, dv by dt is the flow rate or the rate of change of volume, so I just wrote it as q. So q is dv by dt, and the diameter d of the jet. Here is the continuity equation, av is equals to q. So d square by 4 is the radius, pi r square the area, and here we get the velocity as 4q pi d square. Now the F impulsive, we just supply it here. Okay, just put it here and you can get the equation. Okay, so all the rest of the thing is done here. The pressure, the delta F pressure can be calculated from the bottom and the top. The force at the bottom is larger than the force at the top, that's why the disc is floating. Okay, the force at the bottom is larger than the force at the top. Okay, so the force at the bottom is P bottom, which is the pressure at the bottom, pi r square the radii of the the bottom face, and small r is the radii of the inner face. Now P naught pi r square is the pressure on the smaller side or the lower face. Okay, you can just calculate this delta F pressure and equate it. You will just get all the calculation, and it is written here. Okay, So if the flow rate is increased, the disk will not sink, and if the flow rate will decrease, the disk will surely sink. It will surely sink. It is damn sure that it will sink. So you can just see that if flow rate dependence, what is the flow rate dependence? You can just say that when the flow rate is reduced, the pressure difference must also be smaller, because the impact of the water jet is smaller. And we can just see that the radii of the hydraulic jump circle will shrink and it will come towards the center, and as it comes towards the center, the water will cover the disk and it will sink. Okay, so the radii is proportional to q to the power 2 by 3. Q is the flow rate, and it is done by a more sophisticated analysis which is done in this video. You can just watch that. I will not explain it because it's not of our syllabus. And confirming that a reduced flow rate causes a faster flowing area around the circle of the disk to decrease in size. Okay, so here I can say that if the flow rate decreases below certain critical value, the disk will surely sink. Now for the students, for Olympiads, you can just do this higher analysis part. The higher analysis part requires Godwin conjecture. Okay, you can just search for that and Google that if you want to really study that. So here the phenomenon, the figure of the phenomenon, you can just see it here. I will just show you. The water is falling from the jet in the form of jet on the bottom of a sink, and here you can see that there is a circular stationary wave formed. There is a thin layer of water in this region, thin layer of water, and there abrupt rise, thin layer, abrupt rise, thin layer, abrupt rise in all the radial direction. So there is a circular stationary wave formed here. So theoretical proofs are for ideal fluids and also for viscous fluids. So this is one another type of proof. You can just study it. I have provided it here. You can just pause the video, write it also if you want to. It is basic proof. Okay, so this is the radii function. Okay, the radii function, you can just also note that. And for a viscous fluid, by using Godwin's conjecture, we can just prove it. This is gravitational acceleration. Okay, here you can see the q to the power 2 by 3, which is the flow rate, and the dependence of 2 by 3. I just proved that here. So I hope you like the video, and if you like the video, just share it with your friends who are my friends too. And I thank all my teachers, and thanks for watching the video.